Okay, so Friedel-Crafts alkylation. Now you see what we're doing here? Right? We did halogenation. How do you spell that? Halogen. How can I misspell that? Halogenation, which was bromination, a chlorination, right? Then we did sulfonation. Then we did a nitration. Now we're going to do, watch this now, watch. This is so cool. Alkylation, right? Shun. So, alkylation. Now, in every case, what we did was we took some mess and we made from it an electrophile. Then, would you pause the video? Pause the video now and predict where I'm going with this story. Okay, let me suppose that you paused it, that you wrote some notes out. I so hope you did. Then what you've got is, watch this. This comes here, bam. If you didn't pause it, we've been doing the hydrogen over on this side, right? Every time. And so I'm going to keep doing that, but watch out now. If you might come across a problem that's set up exactly in the opposite configuration. You don't want to get, married to this one side. Okay, now what's this? What is that? It's the sigma complex, right? So this is in resonance with this. It really would be good for you to draw all this out, including the electron moving arrows. I'm going to put this in brackets. Obviously, our brackets have been, horizontal this whole time. I'm doing it vertical because I'm running out of space. And what happens now, right? Remember, you should write all this out. So anyway, it's been the same thing every time. So we've been making our electrophile. Sometimes I say maybe E star. I'm making up notation here, but something prior. In the case of bromine, the E star was simply bromine, and then it complexed with iron 3 bromide, right? This put a formal charge right here, which was practically shared between these two guys, right? And consequently, the pi electrons attacked that guy, right? Okay, and then these ones went over here. So you should go back and review all of these mechanisms, maybe even before you start this video, because you'll see some similarities, and it will help you, and you'll see some differences, and the differences will help you appreciate the similarities. So, all right. Now that we've got that, can you guess what's going to happen? I'm going to have some leaving group, right? Boom. Boom. And it's going to look just like this, right? So let's begin. So we look at this and we say, do you think that an alkyl halide is effective electrophile? Is this a good electrophile? Right? This kind of looks, by the way, can I draw it in parallel? This is going to be a bit busy. Right? Where this is this, and this, when we were brominating, was coming in there. Remember that? And this went off there? Okay. So it's a similar story. I'm gonna erase that. That's just ugly. Eraser. Boom. Okay, let's go back to pen. I could have just erased all of it, I guess. Pen. Wait, that's not a pen. Here's a pen. Okay. So the question is this a good electrophile? This was perfect for SN2 substitution, right? Remember that? Remember that? This was great, okay? Problem is, it's not quite a good enough electrophile because this is not such a strong nucleophile. These pi electrons are not so good. So let me go back and erase this again. Erase all ink on this line. Still in pen, perfect. Okay, now that we've got that, how did we make this a good electrophile with bromination? We complexed it with a Lewis catalyst. We complexed it with the Lewis acid. Remember that? Let me go back to red. Okay. So we get decent alkylation if we do this with, if we do the same thing with Al. Right. Get very much the same thing. Okay, let's see how that works. So first of all, just like you saw with the chlorine and the AlCl3, this is Cl, and Cl. Sometimes I give up, right? Remember that was in halogenation. Well, we get the same thing, or very similar thing here with alkylation. Stop and say that out loud. With alkylation, so we get a Lewis acid comes in like AlCl3, and the halide complexes with it. Now when that happens, the chlorine doesn't like to have a positive on it, right? So these electrons will go off and you'll be left with a carbocation. What is this? A primary, secondary, tertiary carbocation? Say it out loud. What kind of carbocation is that? That right there, as you see, is a secondary carbocation. In this case, it's secondary. And then the pi system, just a second here. The pi electrons attack the carbocation, just like that. So you get, boom, right? So show the full mechanism. The full mechanism is going to be on page, it's on page 885, but don't go there yet. What you ought to do, page 885, what you ought to do is pause the video and predict what this thing is going to look like. Go back and look at the previous videos. If you step up to the plate, or I guess using the bicycle as an analogy, get on the bicycle and try to ride it, and try hard, and you're going to find that the stuff will become familiar to you. Okay, I'm not going to draw the mechanism out here. It's on page 885. Primary carbocations are too unstable to form. All right, so, and that's no surprise to you. Primary carbocations are too unstable, and so what happens is, well, we get something that happens. So this will work, but the problem is so this will work, but it's not a good synthetic technique because 65% of it goes like this. How? Why? So what happens is you get a hydride shift. Okay? So what happens is this chlorine, chlorine starts to go off. These electrons right here are going to come over here, and that leaves a carbocation in its wake. This is a hydride shift. Another term we've used for this is it's a rearrangement. Okay. And but get used to but look at that and see why we would call it a hydride shift. What is hydride? What is hydride? Please take a second, and if you don't know, pause the video and guess what hydride is. Go back to your nomenclature, because it's very different than a lot of the H's that we see, and it'll help you if you can keep account of these electrons. So show how the mechanism continues to provide the major, or show how it continues in order to result in a major product, which is the major product of this reaction in the previous slide was, this was AlCl3. There may have been more carbons on there, but that's what happens. This is essentially the same thing. How does this happen? Show the mechanism for that. I think that it's not. Good for you. The mechanism is not given in the text, so good for you. You need to write that out. Ask me if you want to see it, but write it out. Bring me your attempt, and I'll show you what it is. All right, so the alkyl halide Lewis acid complex can also be attacked directly by the aromatic ring, and then you show that one. How is the mechanism gonna, if it attacks it directly, that provides the major product, or rather the minor product, and you draw that mechanism out, bring it to class. Why might the hydride shift occur more readily? Why might that happen? That's another good question. Okay. And then the final question is another one. Another good one. Why are the reactions that give mixtures often impractical? Why don't we want those? They're not good. We don't like it. Why is that? Okay. So there are three major limitations to Friedel-Crafts alkylation. So we're going to add a little spice here now. So first limitation is that the halide leaving group's got to be attached to an sp3 hybridized carbon. It's got to be sp3. Okay. What's the hybridization of this carbon here? What's the hybridization of this carbon? Draw an sp. Draw an sp hybridized carbon. What's going on here? Draw. Draw the full Lewis structure of an sp hybridized carbon that's bonded to a chlorine. Right, so it's only the sp3 that can react as via major Friedel-Crafts alkylation. Only sp3. So one limitation is that it has to be sp3. Another limitation is that polyalkylation can and often does occur. So it's a problem. Okay, we'll show a couple ways to control polyalkylation, but for now it's really two ways to control it. But for now, you know that if you do this, you're going to get oftentimes more. So if I try to put a tert butyl group on there via Friedel-Crafts alkylation, I'm going to get a mixture of products. That plus what else? Just take a minute and write out what that means. I'm going to get that plus what else? All right, and then the third limitation is that some substituted aromatic rings won't give a reaction at all. All right, so this one's not going to give. This is not going to work, and we'll describe later why this is not going to work. Probably you have enough information right now to guess, but for now, some substituted aromatic rings, such as nitrobenzene, are too deactivated to react, and we'll talk about that in more detail. Now, go practice with conceptual connections 5, 6, and 7. Good luck.